All right, in the interest of time, let's go through it. Not that you'd be able to do it that quickly, so keep working through it, but let me show you how I would go about this. It might help you to write this equivalently as 0, 0, tensor 0, 0, so that you have the outer product on either side, and similarly for the other terms. So that's just a notational thing, right? That's what we mean by this notation. There's a implicit tensor product there. Now to evaluate this, it's going to be similar to what we did here. Let's use the computational basis again as our basis of choice to evaluate the trace. So I'm going to get two terms. It's going to be the identity tensor 0, whatever the state is, identity tensor 0, plus identity tensor 1, the state identity tensor 1. So identity tensor 0, rho A, B, identity tensor 0, plus identity tensor 1, rho A, B, identity tensor 1. Okay. Now, there's a decent number of terms to write out, but it's pretty easy to look through and just think about. Again, you just have to use two properties. 0 inner product 0 is 1, and 0 inner product 1 is 0. So you're just sort of looking through this equation and inspecting where it will be 0 and where it will be 1. And what you'll actually end up seeing is that you'll get 1/2, 0, 0, plus 1/2, 1, 1. This will be the state of Alice's qubits for Alice and Bob sharing a joint state, this entangled state, one of the Bell states. Now, this is very interesting. This is so interesting that we give it a definition. This state is known as a maximally mixed state. The maximally mixed state of a qubit is identity over 2, which of course you can write in the same way using the resolution of identity, 1/2, 0, 0, plus 1/2, 1, 1. So that's our definition of the maximally mixed states. Why maximally mixed? Well, it's because we don't know, in the largest sense, which we can define using entropy once we get there, whether we have the state 0 or the state 1. Okay? So it means that the coefficients are all equal, and there's an equal probability of getting 0, 0, and 1, 1. So this is the maximally mixed state. In a way that I'll explain to you next time, we can also define a sort of quantity of entanglement, and this will be a maximally entangled state. Maximally entangled state. So what you just showed, a very famous calculation in quantum information and quantum mechanics, that the partial trace of the maximally entangled state is the maximally mixed state. What does that mean without all this vocabulary? It's a very strange thing, because in the maximally mixed state, I'm the most unsure of what we have. I have an equal probability of the state being 0 and an equal probability of the state being 1. Okay? In the maximally entangled state, this is a pure state, though. So I'm able to describe the state itself fully. I'm able to say that the full state of the system is 0, 0, plus 1, 1 over root 2, right? There's no ambiguity there. But if I try to evaluate what either component state is, I'm the most unsure. It's the maximally mixed state. So it's a very strange thing. Do you know any other theories where you can write down the state of the full system, but you can't write down the state of any component part? It's a very quantum mechanical type of thing. Very famous calculation. Partial trace of a maximally entangled state will give you the maximally mixed state. This will be true for Bob's qubit as well. So as extra practice, you could try to show this for the trace over A of rho AB. You'll get the maximally mixed state as well, 1/2, 0, 0, plus 1/2, 1, 1.